Okay, welcome back. All right, chapter 6, parts of the periodic table. So they're going to talk about the transition metals. And first, what's called the inner transition, which is the D block. So again, this is called inner transition metals. And then the lanthanides and actinides are called outer transition. So the D block is inner transition. F block is considered outer transition. Okay. And the characteristics of these transition elements is that they have sublevel to energy level overlap. And we already said in chapter 5 that we had an overlap between the 4s and the 3d. That even though the 4s had more quantum energy, the 3d has more total energy because of the angular momentum that's imparted by the fact that there's 10 d electrons and only 2 s electrons. So because of this overlap, we get multiple valence, which means multiple charge numbers, depending upon the situation. So that's one of the properties of transition metals, multiple valence. Another rare thing about transition metals is that they tend to, although this is not always correct, form brightly colored compounds in solutions. Now, in chemistry, most of the time you're dealing with white solid crystals or colorless liquids. But with transition metals, we get a little variety of color. Let's take a look at that. So here's some pictures I stole from the internet. One of my favorite transition metals is manganese, because there's actually 5 different colors that you can get from manganese depending upon its oxidation state. For instance, the purple one here is manganese 7. But again, it depends upon the charge, giving you different colors. Now, the reason why it gives you colors has to do with something called crystal field splitting or crystal field theory, which is well beyond the scope of Chem 1 honors. I mentioned it a little bit in AP Chem. We're not going to worry about it. Again, all we need to know at this point is that transition metals oftentimes form brightly colored compounds like these paints: cobalt turquoise, manganese blue, cadmium red. So at the base of these paints are solids that come from those compounds. Now, the outer transition series, the lanthanides and actinides, these are what we call our F block elements. They're often referred to as rare earth elements, and they're called rare earth elements because they compose less than 1/10 of 1% of all the material in the Earth's crust. Now, that doesn't mean they're not important, but they are rare. Now, with the F block elements, you actually have multiple layers of overlap between the S, the D, and the F shells. So we're never going to do configurations at this level involving that because you would have to understand crystal field splitting. And other than memorizing it, there would be no way for you to predict it at this level. So you just have to know that they exist, that part with the 4F and 5F, that those are called either rare earth elements, outer transition, or lanthanides and actinides. All right. Nature tends towards stability. So when atoms bond, they're trying to release energy. So let's say your electrons cannot get any closer to your nucleus, because that's one way of giving off energy. Well, that doesn't mean to say that your electron can't move closer to a different atom's nucleus. The process of moving a negative closer to a positive releases energy. So it doesn't matter which negatives and positives we're talking about. So a chemical bond is just the positive nucleus of one atom attracting the negative electrons of another atom. So when things bond, they tend to form stable electronic configurations. All right, what does that mean? Well, it can mean a number of different things. Most commonly, it forms a compound following what's called the octet rule, where when you complete your outer S shell and your outer P shell, you become stable. In other words, you turn into a noble gas core. And we talked about that when we did the isoelectronic series. All right, so let's see the octet rule here. If we have oxygen is normally helium core, 2s2, 2p4 configuration. All right, well, when oxygen bonds, it forms oxide. So 2 extra electrons. Where do those 2 extra electrons go? They go into the valence shell. So you wind up with a helium core, 2s2, 2p6, which is the same as a neon core. Nitrogen. Again, helium core, 2s2, 2p3 configuration, but when nitride becomes an ionic compound, it takes on 3 extra electrons, which again gives it the same number as neon. Fluorine becomes fluoride. So fluorine is helium 2s2, 2p5. How many more electrons does it need to fill its outer p shell? It only needs 1 more electron. So fluoride is what it becomes when it bonds, and then it winds up with the same number of electrons as neon. So we call this completion of the s in the p shell, since you need 2 electrons to fill the s, 6 to fill the p, that when bonding occurs, many things follow what's called the octet rule. Total of 8 electrons in your highest energy level. So now we go back to our electron dot diagram. We were taught in chapter 5 that oxygen, 2s2, 2px, 2py, 2pz, and then back to the 2px to complete its configuration. So oxygen is normally helium core, 2s2, 2p4. Well, hydrogen is 1 electron, so it normally has a 1s1 configuration. Well, how does this bonding occur? Well, we were taught in elementary school that the hydrogens are going to share electrons with the oxygen. So when that happens, hydrogen now has 2 electrons. How much do you need to fill the first energy level? Total of 2. So hydrogen has 1 of its own in green and sharing 1 with the oxygen. So both hydrogens have completed their first energy level. We know a full energy level means stable. Oxygen now has 8 total electrons. 6 of its own, right? 6 from its valence shell, and then sharing 2 with the hydrogens that are bonded to it, and that gives me a total of 8 electrons. Again, octet rule. Now, the octet is not the only stable arrangement of electrons. It's the most stable. But it turns out when you have an energy level that has all parallel spins, if you have all parallel spins, then what you have is a half-filled sublevel. Like, for instance, a D5 configuration or a P3 configuration would be considered half full. These have stability as well. And when you have sublevels that have completely paired electrons, we'll call them full sublevels, and those configurations are very stable as well. A D10, let's say a P6 we already know, but F14, for instance, would be a stable configuration. So half-filled shells and full shells are considered stable as well. Now, the bigger the shell, the bigger the effect. For instance, if we said the octet in terms of stability, the octet is more stable than a full sublevel, which is more stable than a half-filled sublevel. It's also the size of the shell. In other words, having a full sublevel, having a full D shell is going to be a bigger deal than having a full S. Now notice I didn't write full P, because if you have a full P, you're following the octet rule. So that takes precedence. That takes priority. But a D10 configuration is much more stable than an S2. An F14 is more stable than an S2. Again, the bigger the shell, the bigger the effect. A D5 configuration is more stable than a P3 configuration, which is more stable than an S1. They all represent half-filled shells, but the bigger the shell, the bigger the effect. Alright, so that brings us to this concept of electron promotion. Now, I hate the term electron promotion. It's a misnomer. Promotion implies that you're taking one thing and you're promoting it. You're moving it to another place, and that's not what happens. A better name for electron promotion would be exceptions. Wait a minute. We're going to say Halffilled violators. In other words, things that involve electron promotion do not follow the Halffilled rule. Let me show you with chromium and copper as an example. Okay. Start with chromium. We're going to do what Halffilled would expect as far as configuration. The Halffilled prediction predicts that chromium would have an argon core, a 4s2, a 3d4 configuration, but this is not what actually happens. When we apply X-ray diffraction to this, our actual configuration turns out to be argon core, 4s1, 3d5. This doesn't happen. This does. And the question is, why does that happen? Well, because with a D5 configuration, you have extra stability. Remember, nature tends towards stability. So we love that. We have a stable half-filled shell if we do that. So chromium will not do 4s2, 3d4, but instead we'll do 4s1, 3d5. If we look at it in terms of an energy diagram, again, I'm going to do the Halffilled in white. So here's the 4s shell. Now it turns out the 3D shell is almost degenerate to the 4s. They're almost exactly the same energy, but the 3D is slightly higher. Just slightly. So this is a small energy gap. So the Halffilled expectation on chromium is that we should have 4s2, 3d4. But what you wind up with, instead of having that electron in the 4s, is actually found in the 3d. Now you have all parallel spinning electrons, which adds stability to the electron configuration. Now, again, they used to call this promotion, or they still call it promotion, but they named it promotion because the original theory was that the electron moved up to the higher energy orbital. It doesn't. It's just found there. Again, it's a misnomer. We'll see the same Halffilled exception for a slightly different reason when we look at copper. Again, what would Halffilled predict? Halffilled would predict argon core, 3s2, oh, I'm sorry, not 3s2, 4s2, 3d9. But you could probably already predict the actual configuration is argon 4s1, 3d10. Why? Because now we have a full D shell. So again, on an energy diagram, it looks like this. Here's what Halffilled would predict. Again, the 3D, almost the exact same energy as a 4s. Now, I haven't included the rest of the energy diagram. I left out all the core electrons. I'm just looking at the valence shell, so maybe I should write that in here. Let's write valence shell. Energy orbital diagram for the valence shell. For copper, we would have expected this, but instead what we get is this, right? I'm going to fill that shell. Full D shell. Extra stability. That's supposed to be an exclamation point. I'm very excited. Okay, so what criteria in order to get promotion? Let's call this electron promotion criteria. One, has to involve energy levels or sublevels that are similar in energy, almost degenerate to each other, and that occurs where we have overlap. So we could have electron promotion between a S shell and a D shell. We can have promotion between a D shell and an F shell. But we cannot have promotion between an S and a P, or from a D and a P. This is too big of an energy gap. So we cannot get promotion there. But between S and D and F, and we're only going to focus on the S and D part. So there's really only 6 electrons, 6 atoms that you have to know for electron promotion. Pardon me. Still not getting over this cold, man. Sorry. Alright, let's go back to the periodic table. Here we go. Periodic table. So if we look at the periodic table and we set up our columns here, here's a D1, D2, D3. Here's my D4 column. These 3 elements in here promote. There is no D4. It's really an S1, D5 configuration. So tungsten, molybdenum, and chromium promote to a half-filled D shell. And the other 3 you have to worry about is copper, silver, and gold that are in the D9 column. There is no D9. It just does S1, D10. So again, instead of doing S2, D4, that doesn't happen. We get S1, D5. And instead of doing S2, D9 in column 11, instead what we get is S1, D10. So there's only 6 elements you have to worry about. Now, there's promotion here between the lanthanum and actinium. But again, that's advanced rare earth metal stuff. Not going to deal with it until you get to your senior year of college. Alright, last part of the video. Metals versus non-metals versus metalloids, groups. I'm sorry, that's for the next video. So I'm going to wrap it up right here. Thank you very much.